Hey there, in this video we're going to look at a special question type which is called literal equations, and within literal equations we will be isolating variables. So in this type of question you'll be given an equation or formula with multiple variables and you'll be asked to solve for a variable. When you solve for that variable, you will not end with a numerical answer. So that's a key thing to note here. You're not looking for something like x equals 7. That is not what we will end with. In comparison, today in this lesson, we will be looking specifically at multiple variables in an equation. So for example, maybe I have something like the Pythagorean theorem, a squared plus b squared equals c squared. And in that scenario, I'm asking you to solve for one of the three variables. So for example, if I asked you to solve for b, you'll be getting b by itself and then equal to whatever's over on the other side, which we'll talk about how we get there. But we'll be just manipulating and using inverse operations on the equation to get the variable by itself. And in that end process, or in the end of that process, we will have an equation where we have a variable that we were requested to get by itself, and then the rest of the variables and numbers on the other side of the equal sign. So that's what we'll be looking at in this lesson. I wanted to give you a quick, simple visual and relate it to something that you have done, looking at linear equations and changing linear equations into slope-intercept form. So here's an example of a basic linear equation that we might have been given, and then changing it into that y equals mx plus b slope-intercept form. That is a specific example of a literal equation. So we're using inverse operations to get y by itself. There's still an x in the problem. There's still other numbers in the problem over here on the right side. But the key thing is that we are isolating the variable. We are getting the variable by itself. That makes it a literal equation. In other words, when we solve for a variable and get all the other variables and numbers to the other side. So again, we're not getting y equals 7 or a number like that. It's just y equals 2/7 x minus 2, for example, here. So we're going to look at how we do that beyond just the linear equation. So we'll start with a quick review of simple ones, and then we'll get into some more complex examples. So let's take a look at reminding ourselves what the inverse functions are for some functions that we will most likely see. So for example, remember the opposite of addition is always subtraction. So if we're looking at an operation of something being added, the opposite or the inverse operation is subtraction. For multiplication, remember the opposite is division. When we have something squared, so for example, x squared, the opposite of that or undoing of that is going to be square rooting. So for example, if I square root a square, they cancel each other out. Just like if I add 7, but then I subtract 7, they're going to cancel each other out. If I multiply by 2 and then I divide by 2, they're going to cancel each other out. So again, the square, the opposite or inverse operation of that is going to be the square root. In a similar concept, the cube, which is, for example, x cubed, raising to the third power, the opposite or the inverse operation of that is going to be the cube root. So those are some key functions or operations that you'll see, and their inverse operations. Something to remember with that, these work both ways. So I put addition, multiplication, square, and cube over here, and these are the inverse, but it also works the other way around. So for example, if we have subtraction in a problem, if we subtract 7 from both sides, if we subtract 7 on one side, then adding 7 to both sides is going to be the inverse operation that undoes that minus 7. So for example, here, if we have divided by 2, the opposite of that or the inverse of that is multiplying by 2. If we have a square root, the inverse of that is squaring it. It will cancel that out or undo that. The opposite of cube rooting is cubing. So it goes the other way around as well, just something to keep in mind moving forward. Another thing that comes in play that I just want to take a second to review quickly is that when we're solving equations, we don't work with order of operations going down this list like we typically do. We actually are going to start with our addition and subtraction, and we're going to address the addition and subtraction, then we address multiplication and division, then we address exponents, and then we address the parentheses. So we start at the bottom and we work our way up when we're solving equations. If I was just given an expression, for example, 4 plus 7 squared minus 2 divided by 6 plus 14, something like that, then we're going to be working through our parentheses, then our exponents, then our multiplication and division, then our addition and subtraction. But if we are solving an equation, we're doing the opposite of that. So we are doing the inverse operation. So we are going backwards. We're addressing the addition and subtraction first, then multiplication and division, then exponents, then parentheses. So we are going through that reverse order of the order of operations. And then one other note I want to make: once you get up to the parentheses part of it, once you're working within those parentheses, you are going to be restarting the order of operations from the bottom again. So once I get, for example, if I get a set of parentheses equal to some other stuff, to get whatever variables in the parentheses by itself, we're going to have to restart down here at addition and subtraction. And we'll see that in one of the examples here in a minute. All right, so let's take a look at two more basic examples. So we have A equals 4B plus C, and we are going to solve for B. So I like to highlight the term, not just the letter, but the term with the B, or the variable we're solving for, in it. That way I can visualize and see, okay, anything else that's outside of that highlight is going to need to move to the other side. So in this case, that C is going to need to move to the other side eventually. So if you think about your order of operations, I like to write it out, especially as you're getting used to it. Start at the bottom and go up. So addition and subtraction. All I'm looking for is, in order to get this 4B by itself, do I need to get rid of addition or subtraction? Yes, I do. So I see this plus C right here. Plus C is addition. The inverse operation there will be subtraction. So I subtract C from both sides to keep it balanced. C minus C is 0, so that cancels out. A and C are not like terms, so we're just going to write them as A minus C equals, and then 4B. So that covers our addition and subtraction. There's no more addition or subtraction over here with the 4B that needs to move in order to get B by itself. So now we move on to multiplication and division. For multiplication and division, I would look and see, is there any multiplying or dividing that would need to be undone to isolate the B? So now that we have that B term, 4B, isolated, just look at B. 4 is being multiplied by B. So we're going to do the inverse of multiplication, which is division. So we divide both sides by 4. 4B divided by 4 is just going to be B on that right side. A minus C, again, are not like terms, so we can't simplify there. A divided by 4 and C divided by 4 are not going to simplify, so we can just leave this as A minus C over 4. And therefore, we know that our B is equal to A minus C divided by 4, and that would be your final answer on number 1. Let's take a look at number 2. So J equals 10 plus 2 times K plus 3. I'm going to write out my order of operations again so that I can remind myself. And we're going to start from the bottom and work our way up. So we have our first goal is to look and figure out what letter do we need to get by itself. In this case, it's K. Now, K, the term that K is technically in, while it is just the K right here within K plus 3, we're going to have to start by getting this set of parentheses isolated first. And in order to do that, we're going to have to start by getting the 2 with the parentheses isolated first. So in order to do that, we're going to have to get rid of this 10 that's being added to that 2 times K plus 3. And that will satisfy this addition and subtraction piece down here that we're looking at. So we're going to subtract 10 from both sides because 10 is positive. So we're going to subtract 10 to get rid of that 10 on the right side. J minus 10 equals 2 times K plus 3 is our next line of work. Now, we can't actually put the J minus 10 together because one has a J, one doesn't. So they're not like terms. So then we go ahead and we move on to our next step. So we did our addition and subtraction. Now we see other addition, but remember that's within parentheses. So we can't address that until we get up to the top of this list with the parentheses. So outside of the parentheses here, we don't have any more addition or subtraction on that right side. However, we do have multiplication. So there's two ways you could approach this. You could distribute the 2 and you get 2k plus 6, but then you're going to have to do some moving the constant and then dividing. So another option is also to look at this, like I was saying, with k plus 3 not being able to be touched quite yet until we get up to the top of that order of operation list with the parentheses. So instead, we have 2 times this k plus 3. The opposite of times 2, or 2 times, is dividing by 2 on both sides. So we can divide by 2 here, over here, and over here. So that 2 divided by 2, that is 1, and that cancels out. I don't need to write 1 times k plus 3 because that's just going to be k plus 3 if you multiply by 1. So really that 1's not needed. Additionally, now that that's our only thing over on the right side, we really don't need the parentheses either. You can put them if you'd like to, but you don't need them. And then over here, you kind of have two options. One option is to write j over 2, and then negative 10 divided by 2 would become negative 5. Or you can leave it as j minus 10 over 2, since both terms on top are not divisible. So for now, I'm going to leave it like that. And then I want to go ahead and check off the fact that I got all my multiplication and division out of the way. And now I just have this set of parentheses right here, k plus 3 left on that side. There are no exponents, so that one doesn't need anything done. Then we're up to our parentheses. Now, this is where once we get our parentheses isolated, then we need to go ahead and restart at the bottom within those parentheses. So we'll start over with addition and subtraction, then look for multiplication and division, so on within those parentheses. So k plus 3, we're still trying to get k by itself. So the only thing we see here is that plus 3. To undo that, we subtract 3 from both sides. So when we subtract 3 from both sides, we have j minus 10 over 2. And then that minus 3 goes afterwards. Remember, it can't just go on top because this is a fraction with 2 in the denominator. And if I try to subtract up top here, I'm not actually doing what's mathematically correct when I'm subtracting 3. If you wanted to move it to the top, you would actually have to change this 3, this whole number 3, right here, into a fraction with a denominator of 2. So you'd have to move it or change it into 6 over 2, and then you could put the minus 6 on top. But you can't just do minus 3. So it's not necessary. I just wanted to explain how you would have to change this 3 if you wanted to move it to the top of the fraction. But again, in these problems, I would suggest you just write the minus 3 afterwards and then equal to k. And now we see that k is by itself. And so we can, if you want to rewrite it on the left side, k equals, that's typically how we see it, but technically it's not wrong to leave it like this. So that'll be j minus 10 over 2, and then after that fraction we have minus 3. All right, so now we have some slightly more complicated examples where we get into a little bit more than just the linear example like we just did. So p equals 4 plus r minus 1 squared over 16, and we're solving for r. So r is up here. The first thing we want to do is get the term with r in it by itself. So that's going to be this fraction. So we're going to use our order of operations again, just like we've been doing, and approach it the same way from the bottom up. So addition and subtraction, we want to start by getting this part by itself. So we're going to get rid of this 4 by subtracting 4 from both sides. So we have p minus 4 equals, and then r minus 1 squared over 16. At that point, we did addition and subtraction. Now you might think, oh wait, but there's minus 1 here. We can't get rid of that. It is in the parentheses and it has an exponent on it. And it's in a fraction. So for multiple reasons, we can't add 1 to both sides right now. We need to continue to follow these order of operations. So we can't address parentheses quite yet. We're just addressing the stuff on the outside of the parentheses. So we did addition and subtraction, so now we're going to go ahead and go on to multiplication and division. So if you look at this r that we're trying to isolate, it is part of parentheses and that exponent there. It has divided by 16 on the bottom. If it's got divided by 16 on the bottom, we have to undo that with the opposite of division. So that's going to be multiplying by the 16 on both sides. Now, if I just write 16 times p minus 4 like this, that's only being multiplied to the p. Technically, it does need to have parentheses around it so that I notate that it is 16 times p minus 4, not just times p. So when we multiply by 16 on the right side here, it cancels out the divided by 16. On the left side, you could distribute through, but I would actually suggest just leaving it for now, especially because there is a square over here. Eventually, we'll have to undo that square by square rooting, and it helps to just have that 16 separate for now. If you distributed through, you would just have a little bit of a different way of thinking about it in the future steps. That would make it, for some people, a little harder, so I would suggest just leaving that 16 in front. So we have 16 times p minus 4 equals, and then r minus 1 in parentheses squared is left on the right side. So that got rid of, on that right side, the division. There was no multiplication there. So now we can move on to exponents. So we can get rid of or undo that exponent of the squared right here by square rooting both sides. So when we square root both sides, that square root cancels out that squared. And so we just have r minus 1 over here on the right side. On the left side, we have the square root of the 16 times p minus 4. And when we square root the 16 times p minus 4, we can separate that into the square root of 16 and the square root of p minus 4 because we left this as separate multiplication and we didn't distribute that 16 through. I can't break this p minus 4 into the square root of p minus the square root of 4. It doesn't work that way with addition and subtraction. But if we have multiplication between pieces, those pieces that are being multiplied can be broken up. So the 16 can go on its own and the p minus 4 can go in its own square root. So that helps us because the square root of 16 is just the whole number 4. And then we have the square root of p minus 4 and then equals r minus 1. So that is how we undo the exponent. And once we have that exponent undone, then we can go on to the parentheses. And again, we didn't technically need these parentheses here around r minus 1 anymore because it was the only thing remaining on that right side. So now we are able to get r by itself. And to get r by itself, we are working within the parentheses technically. So again, we're restarting at the bottom and working our way up. So r minus 1, we're going to add 1 to both sides. And a common mistake I see on these types of problems is that people turn this into 5 square root p minus 4. 4 square root p minus 4 is a term. It's being multiplied here, so I can't interject that plus 1 and add 1 to that 4. I just either have to tack it on to the end or before the 4 times the square root of p minus 4. So I'm just going to write 4 square root of p minus 4, and then after that will be plus 1 equals, and then r on its own over here. So again, if you want to, you can always flip it around to have r equals on the left side. Don't have to do that, but a lot of people like to write that r equals or that variable equals on the left side. So we have 4 square root p minus 4 plus 1. So that one was a little more complicated, and number 4 is also going to be a little bit more complicated. So let's take a look at number 4. And 4 is really more complicated, not necessarily because it has a ton of steps, but more so just because they're all variables here. And so there's quite a few variables that we're working with. And we are solving for a variable that's in the denominator this time, not the numerator like on the last one. So let's go ahead and still approach it the same way. So we're going to start with our order of operations. Please excuse my dear Aunt Sally. And we're going to start from the bottom up. So again, we're going to start by highlighting the term that has that variable that we are trying to isolate. So in this case, it's going to be MA over Q, and then we have the plus Z over Y. So we are going to start with addition and subtraction. We are going to subtract Z over Y from both sides. when we do that, that cancels out this z over y over here, and we have TB minus z over y equals MA over Q. So that's step one, and that is addressing our addition and subtraction outside of the term that has Q. Now that we have the term that has Q isolated, and by that I mean there's no more addition or subtraction after or before it on that side, we can move to multiplication and division. Now, this one's a little trickier in how we approach it because Q is in the denominator. So we are going to multiply or divide. We're going to get rid of that division of Q, but it's going to seem counterintuitive because we are trying to get Q by itself. But you're going to see that in order to get rid of that Q on the bottom, we're actually going to be moving it to the other side, which will seem confusing at first because we'll say, well, why would we move it over with more variables over here? But you'll see why in a minute, why that helps us. So when we have this fraction here, we're going to undo the divided by Q by multiplying both sides by Q. So over here, we multiply by Q, and then over here, we also multiply by Q on that side. So I'm going to write on the left side Q times TB minus Z over Y. Again, just like the 16 over on the last example we did, I'm going to leave it out front, the Q out front for now, and not actually distribute it in, just because it will actually help us in the next step to do that. So we have Q times TB minus ZY equals, and then divided by Q and times Q undo each other, and we just have MA on the other side. Now, we want to get Q by itself, and where it's at right now, it definitely is not by itself. However, we're not having to really start over at the addition and subtraction piece down here right now because we haven't made it really to like the set of parentheses. We need to keep going through our order of operations. So once we get to this point, we ask ourselves, are there any exponents? Nope, no exponents that we can undo. Then ask yourself parentheses. We actually haven't isolated any parentheses yet, so we can't really do that. So you might be thinking, well, what can I do at this point? So this is where once you've gone through that list of order of operations, if that Q is still not by itself, kind of restart the process and ask yourself, okay, how can I get Q by itself? If I'm looking here and I restart at the bottom and I go up, Q, there's nothing being added or subtracted directly to it. We have this set of parentheses being multiplied by Q. So we need to get rid of that set of parentheses being multiplied in that second step here up our chain. So multiplication and division is that second step. That's what we're going to be working on right now. So we're going to get rid of that times TB minus Z over Y by dividing by that TB minus Z over Y. And if we divide by that, it cancels itself out over here, and we just have Q equals, and then MA is on top over here over TB minus Z over Y. And so now we have Q by itself, and so that's how we get the Q isolated in this example. So now we have all the other variables on the other side, and we have Q by itself. And so that's how we isolate Q in that example. So in summary, we always want to use inverse operations to solve for the specified variable. And just a reminder, opposite of addition is subtraction, opposite of multiplication is division, and vice versa for each of those. And then the opposite of squaring something is square rooting. The opposite of cubing something is cube rooting, just as a reminder of some inverse operations. And then we also want to talk real quick about the fact that we start at the bottom of our order of operations and work our way up. So start with eliminating addition and subtraction outside of the term with the variable you're solving for, then go to multiplication and division, then exponents, then parentheses. And remember, when we are working within parentheses, we actually restart and go back up from addition and subtraction to multiplication and division to exponents, and then if there are parentheses within the parentheses, you would go to that step as well. And then finally, remember to only stop when that variable is completely isolated. So that means when that variable is by itself equal to some other stuff on the other side. If it were 2Q equals, that's not by itself. It has to be just the variable on that side to be fully isolated. So hopefully that helps with this topic, and I hope you have a great rest of your day.